Welcome to absolute value functions and reciprocal functions. Lesson number one. So some of you have learned about absolute values before. We'll just go through quick definitions. The absolute value of a real number can be defined as the principal square root of the square of the number. Now, if this seems confusing, then don't worry, just bear with me, and I'll show you an easier way to think about what these absolute values actually mean. So if we look at this example down here, so the absolute value of 6 is equal to 6, and the absolute value of negative 6 is 6. Now what we have here are absolute value bars. And so if you look at these absolute value bars, the value of your number goes in the middle, and in between these values, on either side of this value are your absolute value bars. Now what the absolute value tells you, and the reason why in both cases you have a positive answer, is because the absolute value of any real number will tell you the distance of that number from 0 on your number line, which is why the absolute value of negative 6 was 6, where the absolute value of 6 was also 6. So you had your positive and your negative both giving you the positive number. And if we look at the number line down here, if we look at negative 6 and positive 6, they are both 6 units away from 0. So if you had the absolute value of negative 8 right here, it would be 8. Okay, so let's take a look at some examples here. So we're asked to evaluate each of these values. So I have the absolute value of 3. This is going to be equal to 3. I have the absolute value of negative 3, and again, that's going to be 3 units away from 0, so we would just say that's 3. Now, pay attention to when you have a negative sign outside of your absolute value. This is the only time when you're evaluating, you'll get a negative number. And basically what you're doing is, we know if I cover up this negative sign, I know that the absolute value of 8 would be 8. But what this negative sign means is basically negative 1 times 8. And so my final answer would be negative 8. So another way you can look at that is negative 1 and then absolute value of 8, which would be negative 1 times 8, which would give you negative 8. So it's going to be the same thing here. I have the negative outside, so I know that the absolute value of negative 8 is 8, which will give me the same result of negative 8. Now if I have the absolute value of negative 7 plus 7, this is the same thing as saying 7 plus 7, which would give me a value of 14. 1 minus 5 is the absolute value of negative 4. 1 minus 5 is negative 4. Absolute value of negative 4 is just 4. And then with this one, just take this in steps. The absolute value of the square root of 81, well, square root of 81 is 9. The absolute value of negative 9 is 9, but we do have this negative sign on the outside, so we're basically multiplying it by negative 1, and so that would be, again, negative 9. So remember that the absolute value is just the distance of the number from 0 on your number line. And remember that you'll never have a final answer that is negative unless you have a negative outside of your absolute value signs here. Okay? So let's look at, in this unit, we're not just going to look at evaluating absolute values, but what we're more going to be looking at and examining is absolute value functions. Okay, so how do you graph an absolute value, and what does that mean to have an absolute value equation or an absolute value function? Let's look at this first example. Consider the functions g of x is equal to x and h of x is equal to negative x, and whose graphs respectively have equations of y is equal to x and y is equal to negative x. Sketch and label each graph on the grid below. Alright, so if I have an equation that is y equals x, that tells me that every y value has the same value of x. Okay, so if I have my x and my y's on here, if I start at -2, -1, 0, 1, 2, that means that if y is equal to x, and my x values are -2, -1, 0, 1, and 2, if y equals x, that means that my y value is going to be -2, -1, 0, 1, and 2. All right, so if I begin graphing this, I'm at 1 and 1, 2 and 2, and this is going to keep going on like this, 3 and 3, if I were to continue graphing this. And if it go this way as well, it's gonna look like this. All right, so this is going to be my equation at y equals x. So this is the equation y equals x. Now, what does the equation y equals -x look like? Well, basically, if y equals -x, if again, then I'm going to use these same values, x and y. I'm going to go -2, -1, 0, 1, and 2. If my y values equal -x, then basically what I'm going to be doing for each of these x values is putting them in a negative sign, like that. So in effect, what it's going to be doing is switching the signs. So I'll have 2, 1, 0 will be 0, -1, and -2. So what this is going to look like is 0 and 0. I'm going to have -1 and 1, -2 and 2, -3 and 3, -4 and 4, so on and so forth. And this line is going to continue going down into quadrant 4. All right, so basically, when you have y is equal to -x, then what you're in effect doing is switching the signs around. Now let's see what my next function is going to look like. Consider the function f of x is equal to absolute value of x, whose graph has the equation y equals absolute value x. Complete the table of values and plot the points on the grid and join the points. So if I was at -5, the absolute value I'll be at 5. Because remember, if I was plotting my absolute value, one thing I know is that my y values are not going to be negative. I can't have a negative value. So -4 and 4, 3, 2, 1, 0, and 1, 2, 3, 4, and 5. So what this is going to look like then is if I have a value at -5 and 5, it'll be here. -4 and 4 will be up here. And it'll take this form, which is very similar to my y is equal to -x. On the other side of my 0, I am at 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5. Now I have this V shape that's formed. And the reason I have this V shape formed is because remember that it's just looking for the distance from my 0. If this is a number line, it's looking for the distance from the 0. And in each case, with the positive and the negative, it's giving the exact same distance from 0, resulting in this V shape, and also resulting in nothing below 0, where x is equal to 0. Now, the next thing we want to do is explain the similarities and differences between the graphs on the two grids above. So we want to compare these graphs. So when y is greater than 0, the graph of y equals the absolute value of x is the same as the graph on this side, on this left side. Okay, so when y is greater than 0, so if I have my 0 in my y column here, so when y is 1, 2, 3, 4, or 5, then this graph is very similar to the graph on in this grid here. And I should probably move that down so you can see. So when y is greater than 0, then the graph of y is equal to absolute value x is the same as the graph on the left. Now, when y is less than 0, so at over here, over here, the graph of y is equal to root x. There's no points, right? Because when y is less than 0, it's not actually going to be graphed in my absolute value. So there's actually no data below when y is equal to less than 0. And I should also mention that this side of the graph is also represented here, right? So it's actually a combined graph. I should put that in brackets. Combined graph. Now, next we need to look at the graph of y is equal to the absolute value of x contains two straight lines. State the equation of line 1 in quadrant 1. So we want to state this equation here and state the equation of the line in quadrant 2. Okay, so remember that when we're looking at this graph and comparing to this graph here, we graph these 2 points, or these two lines on this side, on my first graph. And this graph here, we know that this equation, one of the equations is y is equal to x, right? If we compare this side to this side here, we're going to have the equation y equals x. If we compare the other side of this line, of the v, it's going to be y is equal to negative x. And that's something we examined earlier on. And so when we have a graph that looks like this, so it's actually made up of two equations, and it branches off at the x-intercept. This is what's called a two-piece equation, or a piecewise function, or piecewise equation. So we can see from this graph that the equation y of the absolute equals the absolute value of x can be written in two pieces. And each side is going to have a different domain, right? Like this x covers from x is greater than or equal to 0, and x is less than or equal to 0. So complete the following to write the absolute value function. Absolute value of x as a piecewise function. Number 5. So if x is greater than or equal to 0, that's when f of x is equal to x. If x is greater than or equal to 0. If x is less than or equal to 0, that would be negative x. So f of x is equal to x is if x is greater than or equal to 0, and f of x is equal to negative x if x is less than or equal to 0. That was made up by our piecewise function. Okay, so the next thing we're going to look at is investigating the function of the absolute value x minus 3. So f of x equals absolute value of x minus 3. Now, the first thing we want to do is, considering this function, g of x is equal to x minus 3, and h of x is equal to negative x minus 3, whose graphs have equations of x minus 3 and negative x minus 3. We want to complete the values, so these two values here, and then plot the points on the grid. Okay, so when x is minus 3, y is equal to x minus 3, well, all we need to do here is substitute these values of x, so negative 4, negative 3, negative 2, substitute all of these values into this equation here. So this first one is going to look like this. It's going to be y is equal to negative 4 minus 3, so y is equal to negative 7, and we would fill that in right here, negative 7. Negative 3 and negative 3 is going to be negative 6. Negative 2, negative 3, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, and 2. Again, all I did was I substituted these values in for my value of x minus 3. We're going to do the same thing here, but remember, essentially all that's going to happen is that the sign is going to change. So instead of having negative 7 here, I'm going to have positive 7, 6, 5, 4, 3, 2, 1, 0, negative 1, and negative 2. Okay, so the next thing we want to do is plot the points on the grid and join the points, and then extend the graphs. Okay, so let's look at this first equation. When x is negative 4, I'm also at negative 7 down here. At negative 3, I'm at negative 6. Negative 2, I'm at negative 5. And my graph is going to go up like this. Now, with my next, and actually let's connect these lines here. Now, for my next equation, y is equal to negative x minus 3. I'm going to start at negative 4, but this time I'm going to be up at positive 7. I'm going to be at negative 3 and up at 6, positive, and it's going to go down in the opposite direction. So there I have my two equations which have helped form that line, or these two lines. And when we write these equations, we should really label them. So that's y is equal to x minus 3, just so we don't get confused as to what is what when we go and write our piecewise equations. Negative x minus 3. Now, number 2, consider the function of the absolute value of x minus 3, whose graph has the equation y is equal to the absolute value of x minus 3. Complete the table of values, and then plot the points on the grid, joining the points and extending the graph. Okay, so when we're at negative 5, if I plug negative 5 into here, remember that I can't have a value, if I have a value of negative 5, the absolute value will just be 5. So negative 5 minus 3, if I put that into my absolute value, x minus 3, that's going to be the absolute value of negative 5 minus 3, which would be absolute value of negative 8, or 8. If I do the same thing with the 4, negative 4 minus 3 would give me the absolute value of negative 7, which would be equal to 7. Sorry, I should have said that's equal to 8. Okay, so 8, 7, and because you can kind of see the just the trend this is following, we'll just go down like this: 6, 5, 4, 3, 2, 1, 0, and then negative 1 and negative 2. Okay, so the next thing we do is complete the table of values and then plot the points on the grid, join the points, and extend the graph, just like we did over here. So when I'm at negative 5, I'm going to be way up at 8, which is going to be up here. Negative 4, I'll be at 7. 3, I'll be at 6. And it's going to follow something like this. And then once I'm at 4, I'm going to be going to negative 1. But remember that I can't be at negative 1 on the y values because this is an absolute value function. And so it's not going to dip below into the negatives. So it's actually going to go up like this. And here you'll see that we have a combination of our piecewise functions. Okay, so the function f of x is equal to the absolute value of x minus 3 is written below as a piecewise function, but the domain for each piece has been omitted. So use the graph of y is equal to x minus 3 to determine the domain for each piece and complete the piecewise function form of f of x is equal to absolute value of x minus 3 shown below. So basically when we're looking at the domain, we're actually looking for where the x-intercept is. Okay, so this time we can see that our x-intercept is right here. So our x-intercept is going to be at x is greater than or equal to 3 or x is less than 3. So if f of x is equal to x minus 3, so this is when x minus 3, if x is greater than negative 3. If x is greater than or equal to, positive 3. F of x is equal to negative x minus 3 if x is less than 3. So here we see that x is less than 3, and we had it equal to our function of x is equal to negative x minus 3. Okay, so that's what the function is going to look like, or the graphs for the functions of the absolute value of x minus 3 right here. Now, finally, explain how the equation of the second piece can be determined from the equation of the first piece. So basically, the equation of the second piece, basically it's just the negative. It's the negative of the first piece. So using these two lines as an example, I was able to, using my information of y is equal to x minus 3, I was able to come up with the points up here above. And to get these points, basically all I did was take the negative of these. See, if I take the negative of negative 7, that's going to be positive 7, so on and so forth, all the way down. So to get that second equation, all you're doing is taking the negative of the first equation. So next thing we're going to do is explain algebraically, without using a graph, how the domain for each piece could be determined. So if we're looking for the domain of the piece, all we need to do is find the zero of the absolute value function. So when I say find the zero, all that means is if I have an equation, let's say y is equal to x minus 3, for example, and that's the one we just looked at. So if I have this equation, all I really need to do is find out where the zeros are. So if I equate this to 0, 0 is equal to x minus 3, I can determine where my my domain is going to be based on solving for x. So if I solve for x here, I'm going to get a value of 3 is equal to x. And now, depending on where that x-intercept is, that's going to tell me whether or not x is going to be greater than or equal to 3, or if x is going to be less than 3, like it was in the previous case. So we're looking for where our absolute value function is divided into two pieces. And that'll tell us where our domain is going to be. Okay, now you've seen that every absolute value function can be defined in pieces, into two pieces. Now we want to look at these examples and express our absolute values as piecewise functions. So if I have f of x is equal to the absolute value of 3x plus 2, then I know that this absolute value is made of two pieces and two equations. So we're going to use our curly brackets here, but our absolute value is going to be made up of 3x plus 2, and remember, the other side is going to be the negative of that, of negative 3x minus 2. Or you could say the negative of 3x plus 2, where this is in brackets. All right, so in this case, 3x plus 2 is greater than or equal to 0, and 3x plus 2 is less than 0. Now, one other thing we want to do is find out where our x's are, where it's going to cross the x-axis. And in order to do that, all we need to do is equate our equations to zero. Okay, so f of x, 3x plus 2. If I set this equal to 0, I'm going to have to bring this to the other side. Negative 2 is equal to 3x, and x is equal to negative 2/3. And so in this case, x is going to be greater than or equal to negative 2/3, and x will be less than negative 2/3. All right, so I want you to try doing this on your own, and I will homework check this question in class.